Good catch. Thank you to the person who said that. All right, let me just go through that again quickly. So we're just looking at types of classification problems. So again, you can have many possible labels where only one is correct, such as allocating stars to a review, or a binary classification, which is where you only have two possible labels. And in that case, the nice thing about binary classification is you know that there's binary cross entropy rather than general cross entropy. Binary cross entropy is has the benefit of kind of backpropagating gradients a little bit better than normal cross entropy. Not something to really focus on. But the spam, not spam filter in your emails is one example of this. And then lastly, you get to text classification problems where multiple labels are viable. So for example, if you want to automate putting hashtags on the end of tweets. In general, the data sets that you can come across vary quite a lot. So for example, they can vary by type. So in all of these types or all of these quantities of labels that I just described, you can get other types of data. So for example, sentiment or question allocation or topic allocation. The guys on, you can hear me now, right? It is working. All right, thank you. Yeah, big thanks to the person who pointed that out. That would have been tragic. There's changes in the number of labels. So for example, if you're looking at just the IMDb reviews data set, it only has 2 labels to it, a positive or a negative sentiment, but something like Yelp reviews or SST data set has 5 different labels to it. And you can break it down into 2, but it's now it's like an option in terms of what you want to actually get out your model is how many labels we're going to actually use for it. And then lastly, one of the big ones and one of the important things to consider is how much training data we actually have. Usually we end up using data sets that we can scrape quite easily from the web without having to, automate too much labeling or anything like that. Without having to automate too much labeling or anything. So for example, Amazon reviews, you can get 3 million training data sets with a test set of 650,000. You're obviously, in that case, if you want to train a really good sentiment model, you're going to lean towards something like that if you have the scale to work with it. The corresponding downside of that, though, is that the Amazon reviews data set tends to be quite a bit smaller than the others, where if you're looking at IMDb reviews, they tend to be longer, but have less data points. So there's trade-offs. And again, if you're looking at something like a transformer, which we're going to come to, the original instantiation of a transformer had position embeddings which told you where in the sentence, like which index in the sentence your word came from. And so if you wanted to generalize well, you're going to have to train it on longer bits of text so that it can start to learn how those position embeddings work. And so in that case, you might actually choose the IMDb reviews dataset because it has a longer length of training data or kind of example, it has longer examples in its training data. Okay, so these are all depend on what you want your model to do, and you need to pick your data very, very wisely. And I think, obviously the point of that first lab is to start to make that point, at least with the word2vec, right? You're going to hopefully start to see that just even what words you show something as simple as a word2vec model will kind of impact the semantics you extract from the particular words. And that becomes even more true when you're not dealing with something as common as words, and you're dealing with something far more rare and specific, like individual sentences. Okay. So here's an example of the SST data set. You can say ultimately it feels empty and unsatisfying, like swallowing a communion wafer without the wine. In this case, the label is 1. So there's obviously you're going to map on the index of a particular label onto some kind of sentiment, 1 being bad in this case. And you can see on the right here is like a semantic parse tree, which is one of the very kind of classical ways of representing these things. So on the leaves over here are the individual sentences. Sorry, I missed the without. On the leaves of the tree is the sentence, and you're going to try and do this hierarchically, and how you it's almost like a decision tree. How you choose to descend the tree is going to impact how you hierarchically represent the sentence. So in this case, the right subtree was pretty semantically, or at least, semantically meaningless. Like wine doesn't really have a set connotation to it. It's not good or bad, it depends on the context. Probably same with communion wafer and all the other. However, on the side here where you have unsatisfying and empty, those typically tend to be correlated to something that is a little bit more negative, particularly the word unsatisfying. And so you have to build this up hierarchically, where maybe only at the kind of level of multiple words on the right-hand side can you start to say, well, that sub-sentence now, the sentence swallowing a communion wafer without the wine, that has a sentiment of 2, and so on. And then eventually it just, back propagates up the tree until you get to the fact that the whole statement was about a sentiment of 1. We don't really use these anymore, but if you did kind of work curious at least what was going on there, that's kind of the idea of what we want our models to be doing, is starting to identify phrases within the text that themselves give us meaning and themselves kind of in combination allow us to label our data sets. All right, IMDb reviews, that's positive or negative. So you can see the a review here for a movie. Let's see if we can get some sentiment. This movie gives Mike and the bots lots of ammunition to pull some of the funniest one-liners they have ever done. If you try to watch this without the help of Mike and the bots, God help you. So eventually it ends up being negative, but you can see there that if actually all you did was read that bit in isolation, this movie gives Mike and the bots lots of ammunition to pull some of the funniest one-liners, then you might actually start to say, well, sentiment is overall pretty positive there. If I just read that sentence in isolation, I'm leaning positive. But only then when you get to the bottom here, do you realize that he's actually using it to make something of like a joke at the expense of the movie, and then that's going to flip the label of it. So you can see that ultimately the problem here is that a lot of the times pieces of text are actually not even unhelpful, but entirely misleading. And you need to be able to completely contextualize and completely group the meaning of the sentence as a whole before you can start to do things like classification of tone and sentiment. Okay, then there's another example here, Yelp reviews, same kind of story, same with Amazon reviews. Yahoo Answers is an interesting data set because now what you're doing is grouping it into topics. So again, in your training data set, you'll have a set number of categories that you can group these answers into. Yahoo is kind of nice because at least the website itself was structured around these topics. So in that case, you could automatically label the data. But if you obviously then wanted to be more specific or you needed something else from it, then the Yahoo data set would not be helpful because you just wouldn't have the labels. Okay, but it's also nice because Yahoo Answers comes with the question title, the question content, and the best answer in this case. So there's a number of different things you could use from this data set. So for example, you could do the Jeopardy style case of training where you show it the best answer and the title, and then you say, well, what was the question? What is a question which would lead to that answer? And it turns out that in a lot of kind of modern training algorithms and stuff like that, that kind of pre-training of reverse engineering another aspect of the data is actually really useful. It's not something we'll maybe get into too much in this class, but there's a kind of big area of research at the moment, which is question answering problems, and then ultimately it leads to visual question answering, which is at the intersection of vision and NLP, where they'll show like an image of a red ball sitting next to a blue cube, and they'll ask, well, what is the object sitting next to the blue cube? And then the network needs to answer, it's a red ball. In those cases, you have question, image, answer, and a lot of the times being able to kind of reverse engineer the question from the image and answer is actually a really useful pre-training step. Anyway, that's a more advanced topic. Same story for AG News. You can categorize it into sports, and then DBpedia, you can label it as artists. So there's a lot of different data sets, a lot of kind of cool things you can do with NLP. What I will say is, admittedly, these data sets, they're nice for benchmarking your ideas, but in general, a lot of them have recently become quite solved. And what we're really focusing on now is things like scaling up and actual like language generation, and it becomes more difficult then to also measure competency in actual conversation and stuff like that. So that's a topic we'll come to in a couple of weeks when we actually look at language modeling. But for now, classification from text in isolation on these like short paragraphs is a relatively solved problem. Okay, What you'll notice also about this outline, now's a good time to bring this up. There's a couple of things here like generative versus discriminative modeling and that sort of stuff, and classical methods. I've just decided to take them out of the class. In general, that's naive Bayes, and I think a lot of people would have done that. If you haven't, then it's fine. I can make the points that I think are necessary for naive Bayes in 1 or 2 slides that are coming up. So don't be bothered if that doesn't seem to be coming out in what you're seeing on the slides. I did that rather so I can add a new lecture at the end, or towards the end, about how do we scale up NLP models for like the modern era. Okay, this is the big slide you need to focus on today. If there's one thing you take away from today, it is this, because this you're going to see a lot in the next few weeks. This is the general pipeline of how we do classification on text, okay, on actual corpuses of text. So it's going to look a little bit generic, but we'll make it more concrete in a little bit. There are 2 pieces to us. Firstly, there is the processing step, where we actually take our document and try and find some representation for it over here. We're going to denote that by H. And you can see it says there, the feature representation of the text, I like the cat. And that is end of sentence. So that is the input that we're passing into the bottom there. And then once we're done with the text processing, we now have some vector representation of our document, H. And then from there, we can move on to a classification method, which is just getting the probability distribution over classes. And again, that can be sentiments, that can be topic modeling, or anything like that. Okay. And the main point you'll see here is we start off with the feature extractor, and they can be handcrafted or a neural network. And I'll tell you now that the neural network version of this is exactly what we did last week. That was Word2Vec. So Word2Vec is an example of a feature extracting neural network model. It's a fairly, complex one. There are kind of simpler versions, but we'll come to that in a bit. But then on the other side is handcrafted features, which is really before the big machine learning wave in call it 2012. Where the field was sitting, and we'll see one example of that in a second. So classical methods features are extracted manually by the humans, or at least done through some kind of rule. So obviously I'm not going to write a vector for every data point I get, but I'm going to say some kind of rule or some kind of heuristic that can help me represent a sentence or a block of text as a vector. On the other side, neural method, these are feature extractions, and they can learn what is important to represent in a string of text. So we're going to look at one classical method, which is the support vector machine. We're not going to go into detail about actually how the support vector machine works. Again, I think if you've taken intro ML classes, you would have seen this. What I do want us to focus on is what this means over here. All right, so what might manual features have looked like for these early models? And so in this case, it is called the bag of words model. All right. And the second thing we need to see is n-grams. Sorry about the constant announcements at the top. So there's 2 big concepts here that we need to know about: bag of words and n-grams. So in this case, how bag of words is going to work is our vector representation of our sentence. Okay. So this is not our vector representation. This is not our vector representation of the individual words. All right. This is how we're going to represent our sentence to pass that into the support vector machine. All right. And if you don't know what a support vector machine is, just black box machine learning model for now. All right. So in this case, we're going to take our sentence that says, I like the cat on the mat. And we're just going to calculate or count. Sorry, we're just going to count how many times a particular word shows up in that sentence. So for example, the shows up twice. Cat shows up once. Mat shows up once. And on that really small sentence, then we can get that vector representation. Okay. The second thing is that we're going to also use what's called bigrams, which is where we group 2 words together. So I liked the cat, and so on. Every pair of words that co-occur next to each other in the text are going to be grouped together and also treated as if they're one unit in our vocabulary. All right. So now in my mind, the is a word, cat is a word, and the cat is also a word. All right. That is called a bigram. Bi meaning 2, gram for the kind of general thing we add to the end to mean word. All right. So it's a 2 word, so to speak. Okay. And so that is how we now represent our sentence. And first thing, I actually have, I think, 3 questions I wanted to ask about this. First thing, can anyone see a problem with the counting-based method, the bag of words method that we're using here? Guys online, there's a few of you, so you guys are welcome to also answer. Why might counting the number of words in a sentence not be the best way to represent meaning? What's that? It doesn't, the context. That's true. That's one good answer of it. Yes, the words now don't necessarily incorporate context. That's true. There's another reason, but that's a very good point. That is from Word2Vec. What's up? I think you're getting to the right points. Word repetition can be helpful, right? If I say I really, really like the cat, now that's helpful that it's a 2 instead of a 1. But I think you're touching, the fact that you said that is pointing in the right direction. There's another hand. What's up? Okay, you answered my third question. So, and that's going to be one of the next things we talk about in diagrams. So hang on to that thought. There's one other really, really, really kind of detrimental aspect to this. Yeah. True. Okay, so I think I would put that in the same category as the words are not semantic representations. So again, you'll be deceived by representations of stop words because they look as semantically meaningful as the cat. That's fine. All right, those are all good answers. So I think we at least thought about it. So the biggest issue here is that sentence or word order is lost. Okay, so counting based on just whether or not the word is in the sentence has no bearing on how it is kind of represented or kind of how it follows. Now, if I said to you, I don't like, that's obviously different to saying, I like the cat, don't wake it up. You know, that's going to look the same as saying, I don't like the cat, wake it up. Sorry, I'm impressed with the example I just pulled from my mind there. So that's kind of a reason why we care about word order. Now, bigrams fixes that, okay? So we add in don't like as its own thing. So now at least I can disambiguate the sentence representation where I'm saying don't like because that'll give me a 1. Whereas in the sentence that says I like the cat, don't wake it up, that'll give me a different vector representation. It is to the other points now very difficult though, because I'm going to have to start trying to use that kind of one item in my vector representation to disambiguate the semantic of that sentence. So that's a really, really like subtle learning problem. And semantically, as it's been pointed out, it's not, those aren't going to be semantically meaningful in their own right anyway, because it is still effectively like a one-part representation of the words. And then my third question from here was going to be, well, if bigrams kind of fixes this issue of word order, at least within, within a 2-word space, why would we not want to then just use, as you can see, the general concept is called n-gram. So clearly we can go to trigrams and 4grams and 5grams. So why don't we do that? And it was already answered, well, this vector is going to get really, really big really, really quickly. Because if I have 5 words in my sentence, the number of pairs of those words in the sentence is also going to kind of explode. And there's going to be more pairs than there are individual words. And then if I wanted 3 pairings, then that's also going to explode. And so this is now going to run into the curse of dimensionality very, very quickly, on top of the fact that it's just trying to count the occurrence and that it doesn't have any real, as we said, semantic meaning behind the words to try and even see whether or not they're useful or just stop words. So for example, the cat and cat is likely a very, very similar feature for us to use to, determine semantic. Okay. All right, good job, guys. I think we had some good ideas there. All right, so SVMs did better than naive Bayes. In general, naive Bayes also use a bag of words, and it's the same idea. We throw all our words into the bag, we shake it up, we lose word order, and we just start counting how the words show up. In the case of naive Bayes, there was a prior. So, for example, I'll come to you now. In the case of naive Bayes, you would use a prior, which also weights, let's say, how many pages there are in the Harry Potter books, so that you're more likely to pick the 5th Harry Potter book than the 2nd because the 5th Harry Potter book was longer. but ultimately that is kind of the only real distinction. They were still using bag of words. It was still a count-based method. What's up? So it was going to be, why don't we want to, oh yeah, why don't we like the vector representation? Second one was, how does bigrams fix this? Third one was then, what's the problem with just using n-grams? Yeah, I guess the second one was something I ended up answering. Cool. So the most popular H for SVMs ended up being the bag of words, and bigrams, mainly because that was then a good trade-off between, semantic and rich representation, and at least useful representation, and not a huge dimensionality. All right, that's the end of our classical method. So again, the two things we need to take away from that is bag of words sucks because it loses word order, and then n-grams is this idea of putting words together and representing them as their own unit of meaning, which helps when, again, we want to do things like I don't like. Okay, we're now going to move on to the high-level view of neural methods, and again, this is then going to be where we play around with for the rest of the next few weeks and ultimately the rest of the course. So here's the high-level view. Again, we're going to look at our we're going to look at our generic kind of representation of how we do sentence modeling. So again, you start with taking in some sentence and you get some kind of feature extractor. For the moment, we don't really know what they are, although you can probably start to guess. We get from there, we combine the feature representations of our sentence into a single representation as a vector that we can then classify. So classification for neural networks is ultimately going to look like this. We're going to take our sentence and we're going to split it into its words. All right. So immediately that is slightly different. Here on the left, we were thinking of it as the sentence being its own kind of inputs to our model. We're now going to say, well, I don't really want to deal with the sentence to begin with. I'm going to break the problem up and I'm going to deal with my words as inputs in their own right. Okay. From there, I'm going to give each word its own embedding, its own token embedding. And again, the word token there means that that we might be using subwords, we might be combining characters and stuff like that, rather than working on kind of individual words that are white spaced. And for languages that are agglutinative, that is helpful. But in this case, while we're dealing with English and while we're trying to get our heads around the concepts, you can think of tokens as being words. So again, we take in a sentence, we split it by, let's say, white space. We give every word its own embedding. And for now, this can be pre-trained. If you think about just the fact that I took my word-to-vec model from last week, I took that input layer, and whatever that says the vector representation is for a word, that's what I'm going to drop in there. Okay? It's a pre-trained embedding. All right. All right, that's a pre-trained embedding. I'm then going to pass all of these individual vectors. Again, you can see there's no like kind of cross between them. They're all being treated individually at that point. I'm going to pass them into some neural network model, which is then able to combine them into a fixed representation H. And that is a really, really difficult thing to do. And again, it was something that kind of lingered in the weaknesses of our models for many, many years, up to recurrent neural networks and all of those kind of developments on that. Because how do I take something that is variable length down here and always get it into the same size up there? All right. In this case, I've taken, 5 words and a full stop, or 5 tokens and a full stop, and I've given that 4 dimensions in a vector space to represent. What happens now if that was an entire paragraph of text and this kind of went on all the way to the side, and I was trying to now classify, the Harry Potter books or whatever from it? So that's a really, really big difficulty, is how do I compress variable length sentences into a single length vector representation? And ultimately, the architectures we can use for our neural networks are limited by that fact. Okay, and then after that, we then just take this vector representation of our sentence H and we pass it through a linear layer, and we'll zoom on this now. But ultimately, this linear layer is just going to then say, well, I'm taking my H vector representation, it's d-dimensional, so that is a hyperparameter we pick. And again, it's going to depend on things like how long I want my text to be. If I know I'm taking in really short sentences, I could probably pick a small dimensional representation of my sentence. If it's really long, or maybe it's like medical text, and I'm trying to help doctors, automate some of their lives and do triage in a hospital, then I'm going to have a really long or kind of really big vector representation. D is going to be large because I have to represent quite semantically meaningful information in that case. All right. Whereas if I'm not dealing with medical text and I'm just, classifying children's book into genre, maybe there, because the language is easier to deal with, I can make my H representation a lot smaller. That's a design decision. But then from there, I'm just going to take a linear layer of my neural network, so no nonlinearity sitting on the kind of neurons at that point. And all I'm going to do is say, well, I'm taking a d-dimensional vector and I'm mapping it onto a k-dimensional vector. K here is not a hyperparameter. K is determined by my data set. So if I was doing semantic analysis and I only had positive and negative, then it's 2. Positive 1, negative the other. If I'm rating stars for movies, then it's 1, 2, 3, 4, 5. So now I have K is equal to 5 dimensions. So that is going to be restricted by the number of classes in my data set that I have available to me. There's a feather that keeps blowing in here, and I can shit myself every time I see it in my my peripheral vision. So then after we've now mapped the d-dimensional vector down to the number of classes, these are again arbitrary values that our neural network is going to be placing on whether or not, or how likely it feels the individual classes are. And what is left then is to turn those propensities, like we discussed last week, into probabilities. How do we do that? With a softmax. Okay, you take the exponential, now you have only positive values, and so you can then divide by the sum to get a probability out. All right, so it's the same idea of my neural network giving me a propensity and then doing a softmax. That's the same as last week. It's just a different kind of classification problem now. Last week we were doing classification of words. Now we're doing classification into categories or something else. All right, but it's the same idea. I have K number of classes, and a softmax gives me the probability of each class. All right, are we all following for the moment? Yes. Sorry, can you say it again? Oh, so it doesn't actually completely matter that it's linear. The main idea here is that this is just the framework we have in mind. Let's say you had other layers off the top here that were non-linear, right? Then all I would say is that that's now being kind of pushed into that network. Okay, that's not, I guess, a rule. All right, we're happy? We understand the general framework here. We understand the general pipeline on the left, and understand the neural network's kind of general framework on the right. Again, I'll linger here. This is going to come up for the next month or two. Cool. Guys online, we following? All right, less thumbs than before, but we will move on. All right, so this is our general framework for the neural network. So let's just zoom in a little bit on what's happening off the top there. Yeah, what's up, man? Thank you.
You're saying will we just have information about the position, just the endings? Because from what I understand, I think maybe I'm not sure if it's actually correct, but the transformer has some sort of function that has some discrete phase, and then it sums the embeddings of the two, and then it was position embeddings, and then it goes into the now I have that feature representation materials. Isn't that what it does? So then how do you solve that issue there?
So we'll talk about word order in a second. Yeah, what you're saying is true. You are correct. Okay, let's focus off the top for a second, and then we'll come to your question of how do we actually combine word embeddings. So again, we're going to build this out from the top down. So let's say I just assume I have embeddings, token embeddings, and let's assume I have a way of combining them into a sentence representation H. How do I go about classifying it? Well, again, you can just think of it as this linear mapping down from the D-sized vector onto K, where that is the number of classes. So D again is the dimension that I have available to me to represent all semantics that could occur in sentences. All right. K then is the number of classes. So how do I categorize the data into classes? And so D must necessarily be relatively larger than K if you want to encapsulate all the information that is available to you in the sentences. And so then that is just going to project down to my number of classes. We're going to do a softmax to get probabilities for each one. Ultimately, you should be kind of noting that is just what logistic regression does. All right. So in this case, what we're going to do is we're going to take each of our H vector representations, and for every class that we could possibly have in our data set, I'm going to learn another vector that is going to be multiplied by H. All right. On top of that, I'm also going to have a bias value. So that's just a scalar for each class that says generally how biased am I towards one class rather than another. So for example, if H came in here and it was just a zero vector, so semantically completely meaningless sentence, then all of these dot products happening out front here are going to be zero, right? The dot product with any vector that's zero will be zero. And so what I'm left with then is just these bias terms on the scalars here, which will say, well, how likely am I to say one rather than another? And so if we're looking at maybe the Harry Potter books, your K here will be 7 because there are 7 books. And in this case, B5 is probably, it's going to be down there. B5 will be slightly larger than B1 because B5 has, I think, 3 times the number of pages as B1, for example. So if we're just getting a general page of Harry Potter as our input, and ultimately something goes wrong and we can't actually represent the semantics of that page, well, the best thing we can do is just guess based on our individual biases, which are hopefully at least identifying something like page frequency from the book without even understanding the words. But this, idea that H is going to be semantically meaningless, it's a nice thought experiment to understand bias, but hopefully our model will never do something that ridiculous. And so what's going to end up happening is now we're going to take our biases, we're going to update it by how large that W1.H is, right? And so when I take that vector representation, if W1 has learned values that make it responsive to a particular H, that value is going to be large, all right? Let's say W2 is on the opposite, it's looking for something completely different, then this value will be small. And ultimately, when I combine all of those, the dot product for each category's vector plus the bias, I will arrive at a scalar value for each class. That is the propensity of that class. Those values in their own right are relatively meaningless. Okay, they only have meaning when I say that class 1 is larger than class 3. All right, then I can do something like a softmax so that I can now start to say, well, oh, actually it's more probable than class 3. Okay, so again, this is the general idea of a logistic regression. And ultimately, I want to just jump ahead. We know that the dot product between two vectors is largest when they align. All right. So in this case, each dot on the right-hand side here is a data point, and it's their H representation for that data point, right? And then the big arrows are the different vectors that I have over here that are looking for those data points. Okay, so in this case, let's use green so it's easy. This data point and this data point and this data point and this data point are all, can you guys see that all right? So these different data points that are all within this red cluster over here, they are all, let's not use green. Sorry to the people who are red-green colorblind. So I mean that genuinely. So these data points that are kind of hovering in this direction now, their H representations align most with this big red vector over here. All right, popping out in that direction there. Which means that when I go W2 times that data point, I'm going to get a large value for that second category. Whereas this data point over here, this one out here, it's almost orthogonal to the W1 vector over there. So that dot product is now going to say, well, they're orthogonal, so we know that that's going to be close to 0 for category W1. If we look at how it's reacting to W3, well, this data point is all the way out here again. And so now it's in the opposite direction to W3. So I'm going to get a negative value out. Okay. And so ultimately, that's all that our neural network has to do. For a given age, it just has to learn these three, in this case, three, because there's three categories, these three large vectors that point in a direction that will identify the different semantics in the sentence. Okay. And it essentially, you can see it's kind of doing the clustering, which is it's learning to do classification. Okay. And so all we do is we take those three learned vectors in our model and say which ones are pointing in the closest direction to our data points, H vector. And then we say, well, the one that was pointing in the direction the most is our class. Okay. And so if we look at the kind of maths of it, this is exactly what's happening over here. So for every class in our data set, we're going to allocate its one vector over here. So W1, W2, W3, plus its bias term. And so this is ultimately just matrix multiplication by the linear layer, right? Again, the H is being transposed to your product, and then you add the bias off the end. Okay. Is everyone comfortable with that idea of why the linear layer essentially works to try and identify data points in H? All right. Genuinely, anyone have questions on this? Again, it's yes. Yes. Yes, exactly. Every column in that linear layer over here is a vector that is trying to search that semantic space. It's trying to align itself to something in that semantic space. And then based on the different ways these vectors align is what they're looking for in that H representation. And then that'll allow us to kind of identify what's going on. So for example, let's say we have a semantic space. And again, this is our semantic space. All these little dots over here are the different vector representations H for, call it, pages in Harry Potter. Okay. So every dot there is a page in Harry Potter. And so let's say now that our H representation, if it's going up and to the left, what that's looking for is mention of Voldemort. All right. Whereas the bottom right here is the semantic space that's looking for mentions of goblets and dragons. All right. Goblets and dragons is highly, highly correlated with one of the Harry Potter books. I think it's the fourth one. All right. And so now that is at least a semantic, a representation in the space that we can use to identify the books. All right. If we're talking about, spoiler alert, Dumbledore dying, then that's going to be a different direction in our semantic space up to the right here. Okay. This is obviously a two-dimensional representation of what's going on. In reality, we're using D dimensions, which is huge. All right. So in that case, we can usually get a really, really rich semantic representation. And if it's large enough, we can hopefully do a really good job of aligning these vectors with our linear layer to different topics or different concepts in that H space. Okay. So again, to summarize once more, H, semantic meaning from our sentence, the weights, the columns of our linear layer will be looking for different directions in that semantic space. And depending on which one is activated the most is which category we allocate our neural network to. So the next question then is, well, I understand how the linear layer will go essentially looking through the semantic space to find the right category based just on, again, the alignment of that dot product. But now how do I actually get those vector representations? How do I get these weights W1, W2, and W3 here? All right. Because it seems to me that I need to know H to be able to do that, but I probably can't get H without the W1, W2, W3 to begin with. And so because it's a machine learning class, I'm sure you can all guess, what we're going to do is use cross entropy. So we're going to take in we're going to use cross entropy with backpropagation. So we're going to take in a training example. I like the cat on the mat, end of sentence. And we know that the target that we want to give to the sentence is label K. All right, so again, in this case, it is supervised, like the data sets we looked at the beginning, where I can tell you that a movie review got 2 stars on IMDb. Or I can tell you that a page of Harry Potter that I just read out is coming from the 3rd book. Okay? And so coming off of the softmax of our attention head, so again, you can see these little bar graphs over there. That is this part of my neural network here. Okay, so it's the output of my softmax. All we're going to do is make sure that the probability that is highest coming out of my softmax aligns to the target class that I want. Okay, so I just want the neural network to put as most probability on the correct label as possible. Again, I think that's maybe familiar. And what we're going to do is we're going to use the cross entropy loss. And ultimately, we're going to be trying to minimize this loss again because it's a loss. And this will minimize when the neural network puts as much probability on the appropriate class as possible and puts as little probability or puts 0 probability on the incorrect classes. Okay, but we're going to now take these labels, the P stars over here, and substitute them into the front of the loss function over there. All right, so the cross entropy loss is a slightly broader term that wants you to align probability distributions. But in this case, our labels over here are 1 hot. So we know that this P star over here is going to be 1 at a single index and 0 everywhere else. Okay? Which means that this term inside of the sum over here is going to be 0 for all of the indices except for the one index that had the 1 in it. And we know that that is going to be index K. All right, because that's the label we've been given. And so ultimately what this collapses down to is all the terms in the summation fall away, and we're left with 1 for PK. All right? And then all that's left then, if we want to minimize the loss with this one term that's remaining, is to maximize that probability of the class. All right? Maximizing the probability minimizes the loss because of the negative over there. And the log just helps make it stable. All right, so you can see how we can maybe start with something slightly complex, like a cross entropy loss, which is trying to say, match the log probabilities of the correct class. And ultimately what we're left with, because we know that in this case, our classification task has 1 hot labels, all we're going to end up doing is maximizing the probability of our correct class to minimize this loss. From here, you just take the derivative of the loss and do back propagation as you always do with neural networks. Okay, and so if we're trying to put this into our general framework, you're going to be told, here is a sentence, here is the correct label that we want for it. You're going to, again, extract some kind of token embeddings over here. How we get there, we will come to in a second, but you can think of them for now as just being pre-trained embeddings coming out of your Word2Vec. I throw it into some machine learning model, which is now going to give me a 8 representation over here. I'm sorry, I don't know why the slide wasn't full when we got it, but you get to some 8 representation over there, which gets passed into our linear layer up here, all of our W's. Those W's go looking for different directions in the latent space or in the semantic space of my sentence, and ultimately you pass it through your softmax. You get your bar charts over there, and you now say, well, take that and make sure that the bar graph that is on label 4 is has the highest probability. Okay. Yeah, sorry about the slide being somewhat missing. All right, I think that's a really good point for a break. I'm happy to answer any questions if anyone is feeling like they're falling behind on that during the break. But otherwise, I'll see you guys in 15 minutes. Guys online, can you hear me okay? Great, thank you. Alrighty, let's get started again. So just a couple. Cool. Let's just start again. So a couple of questions that came up just to maybe reiterate my points that were useful. So one person just asked, we're talking about a d-dimensional vector. That is this H over here. Okay, so H is your d-dimensional vector. So in this general diagram here, that d-dimensional vector is referencing that. Those are the same thing, all right? So I just want to make that clear. Then there was a question around this notation here for the cross entropy. What does this say? So all that this was saying is that we want to minimize the loss over there subject to these labels. All right, like given that or such that pk is 1 and pi is 0. That's not actually saying that we're minimizing, like those don't go together. So I know that that's maybe a little bit unclear given the slides. That's just the notation. It's minimizing, subject to those are my given labels. And then lastly, just I guess the way one of you guys actually phrased it during the break is, again, the weights that my neural network is learning in this linear layer are these arrows here, the W1, W3, and W2 over there, those big bolded ones. Those are the weights of my network. Those are the kind of features that are getting learned. They are looking for different data points in the space, and all they're going to do is tell you which data point is closest. All right. So in terms of this one here, that data point is closest to the vector W2. All right. It's very far away from W3, and it's very far away from W1. So what's your closest category in this semantic space? W2. And so that's the class I'm going to go with. All right. Dot products are a little bit, they don't exactly do closeness in that way, but if that's a useful heuristic to keep in mind for the moment, then we can go with that. All right, then yeah, train it with cross entropy, do back propagation, and you will learn the weights. Run in queue. Guys online, can you still hear me? I know it says not connected, but it looks like it's working. No. They put the thumb up. Okay. I'm not going to risk it. Sorry, guys. Give me a second just to do this properly. Does he a use someone else's Wi-Fi? Can you hear me again?
Yes, we can.
Thank you, MS. Cool. All right. So let's now look at how we actually go about combining the word representations into vector representations for our sentence. The main point of today, and the first and simplest model that we have is called the weighted bag of embeddings or bag of embeddings model. Okay, they're gone. Okay, so we spoke about earlier bag of words, right? We said that bag of words don't take into account word order. All we're doing is counting the different one-hot representations of our words. Now we're just going to do the very minor extension of it and say, well, I have embeddings. They can come from like word to vec or whatever. I've learned how to map at least individual words onto a semantic in their own right. All I'm going to do is I'm going to add them, right? And it's great because, again, we know, as actually someone pointed out earlier, we know that when we're just doing one-hot representations, there's no notion of distance. There's no semantic to that. So at least now, instead of adding up one hot representations, which is counting, the bag of words counting version, we're now going to at least be adding embeddings, so that we can at least say that maybe the whole hypothesis of this is that the semantic space of my sentence is going to be the semantic space of my words. Okay, maybe I can just add them up, and hopefully, you know, this vector over here, that neuron or that dimension of my word embedding up top here, you know, hopefully that's the dimension that says we're speaking about cats, and this one over here says that we're speaking about really positive things, and then this one's saying that we're speaking about very negative things. Maybe when I add all those different word semantics together, I can just get to the exact same semantic space, but I've now added them all together so that I'm speaking about my sentence semantic. Okay, and now at the top it'll say, well, at the top it'll say that there's that green dimension which says that, wow, the sentence spoke about cats a lot, because I had multiple of these vectors firing off in that top cat dimension. Okay, maybe then the bottom one is going to be a little bit more active across the words, and it's going to say, well, how across all of them, how active were all of these positive word dimensions, and then that'll give me an aggregate, the sum of all how positive my sentence is. Same thing for the blue dimension there, saying, well, I saw a lot of negative connotated words, so I think maybe my sentence is also very negatively connotated. And ultimately, you know, from there, we now just have a vector representation with the same kind of semantics as my word, but now is kind of hopefully combine them into something meaningful. There is then an extension of this, which is as kind of machine learners, we hopefully all start to think of, which is, well, what happens if I weight the way I do my addition? So instead of just saying, well, I'm going to treat every word as if it's equal, maybe I'm going to downweight my stop words, as we mentioned earlier. You know, those are not usually pretty informative, but the word cat, we know Devin likes cats, so we're going to upweight that word, and hopefully that helps me label this data. And a classical kind of way of getting to these weights was known as the term frequency inverse document frequency metric. Okay, so that is shown over here. So what we're going to do is, in this case, I'm going to look at a particular document D. I'm going to count how many times a word shows up in that document. All right, so if we're talking about Harry Potter, I've pulled a page from the entire span of books, and I can see that it says the word dragon multiple times. It says it really, really often. On the flip side, we're going to have the inverse document frequency weighting, which says that count the number of data points, or count the number of books in my book, count the number of documents in my data set, in my corpus. All right, so in this case, how many pages are there in Harry Potter in the entire series? Divide that by the number of pages in my corpus that have this particular word on it. Okay, so in the case of my example with the dragon, on the left-hand side, I've got a page that has the word dragon multiple times. But then on the right-hand side, I now have, of the, I think, roughly 1,500 pages in the Harry Potter book series, only, 50 say the word dragon. All right. I'm then just going to do the log of that just to try and, again, stabilize that fraction. And then I take the product of them together, right? And so what's going to happen is that I'm going to go and look for pages in my data set that do not have the word very often, all right? So if few pages have the word in my data set, it's going to pull this denominator down, which then pushes the entire term on the right up, okay? If on the other side, we're looking at a stop word and I'm looking at the word the, all right, we're going to end up having a very large value for the counts of how many times in my document the word the comes up in, but it also comes up in a lot of pages. And so that's going to push down this fraction on the right. Okay, so really we are looking not only for words that are said often on a given page, but said infrequently across the entire data set. Okay, and that combination then gives us our weighting that we pass into our representation over here. Okay, so this is prioritize words which are clearly meaningful to the current document I care about, and downweight words that are meaningful to every document in my text. Okay, and so ultimately combining them, we're going to look at words that are coming up often on the page that I'm looking for, but do not come up frequently across the whole corpus. Why would we do that? Because that means that this is a really informative word specifically for this document. Okay, it gives me this tailored weighting towards, cat or dragon for the particular document I'm looking at. And again, it then downweights things like your stop words, because the will come up on every page of every book of Harry Potter. Okay, and so in that case, this cardinality at the bottom is going to be roughly the same as the cardinality at the top, and you're going to be getting close to 1, which then is going to push that log towards 0. Okay, again, log of 1 is 0. Okay, so that's the idea of term frequency, inverse document frequency. It's kind of in the name. Again, we want terms that are frequent on a document, but inversely frequent across the corpus. And so that's our first idea of how do we go from word embeddings. And again, we'll just assume we've been given those for now. You can either just add them up, or you can at least add them up with some kind of scalar weighting, where the scalar weighting is, looking for words that are hopefully meaningful to the current page that I'm looking at. But again, we don't like having rule-based ways of weighting things. We much rather do something a little bit more algorithmic. And so what we're going to look at now is our first full machine learning way of going, of finding these weightings and actually going from a vector representation of word semantic, again, our token embeddings over here, into a sentence representation of semantic up top there, which is our d-dimensional vector in our general framework. So let's consider convolution can sometimes be easiest to explain through an image just because it's visually, distinct. Was that a hand or did someone just drop off? No, all right. So if I'm looking at this image up at the top here, all right, we have 5 different images of a cat. It's the same cat, but it's moving around the image, right? If all I cared about was whether or not there was a cat in the image, again, you can see the label there is the same across all 5 images, then I don't really care about where it is. And this is the core idea of convolution, is I don't always care exactly where things are. Mainly I care about their general presence within a data set. All right. We know, as we've just seen, that might not entirely be true. All right. So we know that bag of words, there is a weakness when we ignore position, but convolutions does have a way at least of getting around that or being a little bit more sophisticated to it. But ultimately, in this case, we don't care where the cat is. We care that it is somewhere in the image. Then why don't we process all these cats similarly? So this is the main idea. There's a GIF that you can link to here on the slides. But ultimately, what we're going to do is we're going to take this kind of representation, these 3x3 squares, we're going to pass it over our image, and we're going to look for where it matches the same 3x3 squares in my image over there. Okay? And so in that green square that I've just outlined, you can see that it's actually got the cat's face within it, which is luckily what this sliding tile is looking for. So it's going to go one by one over my image. It's going to say, well, can I see the cat's face up there? And it's going to say, well, no, I can't. So it's going to give you that value there. Then it's going to slide the same thing over here. We're now going to be looking for our cat's face slightly over to the right. And that'll give us that value there. When we get to this 3x3 over here, now it's going to be outlining and looking for my cat's face. You can see a lot of overlap between that green cat I just drew and the black kind of outline on the bottom. And so now we're going to get a really, really high value over there. Okay. And so that is the idea of convolution. Is I'm going to take the same, it's called a filter, right? I'm going to take the same representation I'm looking for, and I'm going to slide it over my input and just see, does it show up anywhere in that input? Okay. One thing I just want to note about this slide over there, it is not invariant, it is equivariant. Reason being is that if I move this cat around the input, this is a subtle point, so take this with a grain of salt. But if I move my cat up to the top right here, let's say, okay, so it's not over there, and I'm sliding this convolution over my image, it's no longer going to find the cat there, it's going to find the cat here. All right. Invariance says that wherever the cat goes in my input, the output, this green block up here, will look the same. Equivariance says that when I change my input, the output changes in the corresponding way. All right, in a kind of clearly interpretable way. And so in this case, when I shift my cat up and to the right, the output of this green block over here also shifts up and to the right. So it is equivariant. It varies equivalently to my input. If I kind of, shift my input, the output shifts. All right, so it's not invariance. What we want to try and get to is get something closer to invariance, but that requires a slight different operation within the convolutional network. Okay, so we're going to apply the same operation to small parts of the input and try and find matches to particular patterns. All right, these will then give us the features that the CNN has extracted. The neural network, hopefully though, I don't want to go and tell it what patterns to look for. And that's why we're using an artificial neural network, so that we can actually let it learn the patterns that it should be finding in the data. Okay, and so from bottom to top of the network, patterns evolve from simple to correlated as we stack them. And we'll come to that point in a couple slides, and we'll look at that more for text. Okay, so let's look at an example. We have three different reviews of a movie, and we want to do sentiment classification. So in this case, it says an absolutely great movie. I watched the premiere with my friends. The movie about cats was absolutely great, and the cats were cute. The movie is about cats running around, and it is absolutely great. In all three cases, it says the word absolutely great, which tells us the semantic. That's what we care about. I don't care that it happened at the start, the middle, or the end of the sentence. I was just looking for the fact that it said it. Okay? Now, again, there is a degree to this, because we know that there's also the phrase from earlier, which is to say, I don't like the cat, or I love the cat. Or as an example, I don't like cats, move it off the chair, or I like cats, don't move it off the chair. Now, in that case, where the parents of those words go up, or kind of come together, that does matter. All right, so I don't like, or I don't like will now be different to like being on its own, and then don't coming later in the sentence. So this idea of not caring about space, not caring about where the words are in the sentence is not entirely true, but what the CNN is starting to tell us is that mainly it's about relatively where the words are in the sentence. Okay, so there are certain phrases that I can move around quite freely, but as long as the pairing of the words absolutely great stays together, that then means that I can treat them equivalently. Okay, and so ultimately we want the convolutional network to try and learn that, because I don't have a rule for it. You can see it's even hard for me to bring up good examples for it off the top of my head. All right, but maybe if I show it enough data, it will start to realize that the phrase absolutely great is useful for sentiment, but where in the full paragraph it comes up, maybe that's less impactful, less helpful. So if a clue is very informative, maybe we don't care much where in the text it appears. And so here's the general idea of how a CNN is going to work on text. It is the same idea as the image, except now, obviously, we're not taking in a kind of full square with a cat. We're now going to take in individual word embeddings. Okay, so again, I read in a sentence, it says, I like the cat on a mat, end of sentence. I'm going to map each of those words onto their corresponding embedding. All right, again, for now, assume I've given you a word to back embedding. We're now going to go and try and find different matches of pairs of embeddings in my sentence that can maybe help me do this kind of classification task. So for example, I might go and look at those three, come on. Pen just died. Okay, so I'm going to go now and I'm going to look at these three Okay, back at it. I'm now going to go and now look for, do these three words over here fit some pattern that I care about? And I'm going to slide this window, these three word embedding pairs, over and over and over. And I'm going to start trying to see, does this phrase that I care about come up anywhere? All right. So for example, if I was looking for the phrase like the cat, then it's going to find those three words when that window slides over there. Okay. And then we're going to end up having a large response, maybe in one of those dimensions over there, one of those vector representations there. All right. So same way I took a sliding window over my image and I was looking for the cat's face. I'm now going to have a sliding window going over my text, and I'm going to look for different combinations of these embeddings that are sitting next to each other. All right. So there is still then an assumption now that words that matter for the sentence will be kind of shown in pairs next to each other. For example, my convolution can't say what's that word, what's that word, and what's that word. All right. It can only look at sequential words and do this sliding operation. Okay. In this case, I think this comes up just now. I want to bring it up now. So ultimately, you might then be wondering, well, how am I getting multiple values for a particular space in this text, right? So if all I'm doing is looking over, let's use my meaningful one. If all I'm doing is looking over there, all right, that's a convolution. My convolutional window is, in this case, 4 by 3, because I have 4 dots over here, 4 dots over there, and then 3 words in the sequence. Okay, so that's my little window that I'm sliding over, is this 4 by 3 window. And it says that, hey, I found the 3 embedding vectors for the words next to each other that I was looking for. So now I'm going to respond with a big value. Okay, let's go back to red for this. So now I'm going to respond with a big value. That's going to give me one value up there. However, it's not the case that all tasks can be done based on one phrase, right? As much as I like the cat, if it's a movie about a dog, I might also want to give it a high rating. Okay, so now I'm going to then have let's get back to this. So we have our one representation firing up top here saying, I found the phrase, I like the cat. But now I have another filter, a second one, looking for the phrase like the dog. Okay, and as much as it was kind of similar over here, you know, those first 2 embeddings do overlap to what I was looking for. It doesn't say dog in that sentence, and so it might be positive. It's just going to be a smaller positive value coming out of that, and I'm going to put that value up top here. Okay, last time, let's say there's now a third convolution, a third kind of phrase that I care about showing up in my sentence, and it says, I'm going to climb the ladder. Now, for whatever reason, we care about climbing the ladder. Okay, and I'm going to look for that sliding window there is now going to come across those 3 words. They don't say anything about climbing the ladder. All of the second word is the same, but that's a stop word, so maybe the network kind of weights that down. Let's say climb a ladder, for example. So now none of those words match. There's going to be 0 overlap, and so you're going to get 0. And so this dimension here, that would be for the green filter, is going to return a really, really low value. And so by the end of this, we now have a vector representation for that, you know, club of 3 words that's really large for like the cat, kind of large for like the dog, and is 0 on the phrase climb a ladder. And so now we've got a vector representation for that space, but we've started to try and extract these kind of combinations of phrases rather than individual words. Okay, and so that's now why you get depth in the next layer coming out of this convolution. Every neuron here is or every value here is a different feature or a different phrase I am looking for in my text. Okay, and again, all I'm going to do is I'm going to say, well, I'm looking for one particular phrase. Does it show up in the first 3 words? Does it show up in the second 3 words, third 3 words, fourth 3 words, so on? Then I'm going to take my next phrase that I'm looking for. Does it show up in the first 3 words? Does it show up in the second 3 words, third 3 words, fourth 3 words, and so on? Okay, so every time I look for a phrase, I just slide it over my text and then say, is it kind of appearing in that space in my sentence? From here, we're going to pass it through a nonlinearity just because, again, it's a neural network and we know that we need that to do cool tasks. Okay. Ultimately, it's going to zero out the kind of negative phrases. So in general, your ReLU activation is going to push your network to only really look for positive firings as that convolution slides over. In general, it's kind of hard to say what like a negative firing from a convolution really means anyway. If I'm sliding a kernel over an image and I'm looking for the face of a cat and it fires negatively, I don't think that means that that's not a cat. That would be a very different thing. So in that case, ReLU makes a lot of sense because it only looks for then positive firings that will say, hey, I really found a phrase I care about over here. Then we move on to what's called a pooling. And now pooling is where we get the actual invariance. So you can see here that if I took the phrase, I like the cat, right? We're looking at that phrase here. That is this part of the window there. So that filter that corresponds to the top dimension of my vector, it fires when it says like the cat over there. But if I was doing a different sentence and the phrase like the cat was sitting over here, then that word would have shown up at the top there, right? My convolution would have said, hey, that phrase I really care about is now here, and it's not over here anymore. All right? So it has, when I shifted the phrase in the sentence to the right, the output of my convolution also shifted to the right. That is then, to write it, equivariant. Okay? I wrote it, but my handwriting's bad, so I don't know if that helped. So when my input changes, my output changes equivalently. But now, as we said, we need to be able to take a sentence as input and represent it in a consistent manner. All right? It needs to always give me the same output. And if I had many more words coming off the side over here, I would add many more vector representations over here. All right? And so now, how do I process that? Because I have a variable number of vectors that I'm still processing at this point. And so the answer is that you do pooling. And pooling says, there's two versions of it. Pooling says, come on, that's out of order. I will come back and just make sure we did cross all these things now in a second. There you go. Pooling says either I don't care where it completely showed up, or I just care about the average of how this feature was represented across my entire text. Okay, so there's two versions. There's max pooling and there's mean pooling. Max pooling says for all of these vectors that I got from my different kernels, right? So again, this top value is looking for one phrase. The second value is looking for another. Third phrase looking for a third value looking for a third phrase. And then the columns here are saying which pair of, in this case, 3 words I was looking for that phrase in. All right. So what I'm going to do now is I'm going to do max pooling, where I say, well, just take the maximum value that I found anywhere in that text and set that to be the one value coming out of my sentence embedding. Okay, and I'm going to do that separately for all of the different filters, right? Filters are these convolutions that are sliding and looking for each phrase. So now, if it said, I like the cat over here, my representation is going to say, hey, I really did see that phrase in my text. Then, towards the right, in a completely different part of the text, I saw the phrase saying, I like the dog. That my sentence is then going to say, well, take the maximum and say, well, in my sentence, somewhere, I did find that phrase, like the dog. Okay, and so you're always taking the maximum activity for a given filter and using that as your representation. Okay, now we've lost that ability to say where exactly in our sentence that phrase was said. But in this case, or again in the kind of philosophy of the convolution, as long as I've taken into account which 3 words next to each other, again, when we're doing that kind of like domey looking thing as we were sliding over. All right, so I've got spatial consistency within the phrases, but once that I've seen a phrase, I don't care anywhere else where it came up in the sentence. All right, that is the whole kind of point of this convolutional neural network. And so now if that phrase shifted over, let's say instead of being the first 3 words over there, I shift the phrase to be 1 word over, this value here, the convolution will shift it. It will vary equivalently, but now the max value is the same. And so the output hasn't changed. So now you get that invariant representation. Okay. However, I varied my input text when I moved a phrase to the right. It didn't matter to the final output of my model. That same value, that value at the top is the same regardless. Okay. And so that's max pooling. You can see it here. Again, the maximum along the first row is 1.2. So I just copy 1.2 along the second row is 1.4. Just copy that across. And I do it for all rows, all filters individually. The alternative is called mean pooling, which is, again, you just take the average along that. Mean pooling is a lot less used, mainly because a neural network layer can learn the mean operation. It cannot learn max operations. Okay. And so it's you use max pooling because you want to actually give it that new ability to do a nonlinear operation like maximum. Okay, so that's the high level idea of all of it. So let's kind of go through the actual slide representation of this that I've just spoken over. So again, you can make the analogy to the image on the left. So you're sliding a window over an image. Now we're sliding a window over the text. Okay. So you have a single value saying that that pair of 3 words is showing up there. Then you're going to do the same thing for that value over there and so on. In this case, your input are the embeddings. And so you're going to say, well, did I see the phrase I like the, and you get a word embedding out of that. And so this is called your kernel size here. The number of embeddings you're looking at a given time, number of words you're looking at in your window is called your kernel size. The kernel is another name for the filter in CNNs. All right. So kernel, filter, same thing. And these are also the parameters of my network. All right. So what exactly this window is looking for, what set of, in this case, 12 values in this configuration over here I care about is going to be learned from the data when I do back propagation, again, the same way you do with all neural networks. Okay. The result is going to then be an m-dimensional vector for m different filters, as we said. And the reason why I don't like going through this immediately is because it gets then to how we do this computationally. But now that we hopefully kind of understand what's going on with the convolution, you can actually represent this as matrix multiplication. And this is why, if you know kind of the early machine learning libraries, they always spoke about tensors, is because actually what we're going to do is we're going to take our input here and we're going to flatten it and concatenate them. So I'm going to take in my 3 word embeddings coming out of, again, word to vec. And instead of actually doing the sliding window, which is, again, how I would conceptually think about this, what we're going to do is we're just going to take the 4-dimensional vector for I, the 4-dimensional vector for like, and the 4-dimensional vector for the, and I'm going to concatenate them. Okay. I now have a 12-dimensional, so K being the number of words I look at any given time, D being the embedding of my my words, right? The dimensionality I use to represent my words. So in this case, 3 times 4 for each of those 4 values gives me 12. So now I have a 12D vector being input to a network. I am then going to do matrix multiplication with a set of weights. Again, in the same idea as a neural network where you're just doing like a dense feed-forward layer in this case. All right, so that's just matrix multiplication, no nonlinearity. We're just going to do matrix multiplication here. And the size of this layer is going to be K times D. So again, the size of my flattened or concatenated inputs times by M, where M is the hyperparameter I'm choosing, which is the number of filters. So again, M is the number of phrases or the number of concepts that I am able to identify in a sentence. All right. So again, this first value is going to say, I like the cat. Then this one's going to say like the dog. This one's going to say climb a ladder. Okay. But in that case now, each of these columns of your weight matrix, it's in a different color, is going to be looking for a different representation of that phrase in this input vector here. Okay, and again, we just spoke about how dot products work. We know that when they point in the same direction, you get a large value. When they point in different directions, you get a small value. And so now when this phrase here, I like the, when that 12-dimensional vector is pointing in the same direction as one of the columns of W, I'm going to then get a really big response out of that dot product. What does that mean? That means that whatever phrase this column was looking for was found in this text, all right, in those 3 words. One of the main differences here, though, to keep note of, is the dimensionalities here. Because the input, the size of my input to the kind of whole processing is not K times D. It's not just 3 words. I have lots of words. I'm only going to consider 3 at a time, though, right? And then I'm going to apply this same W matrix multiplication at all kind of different 3-word pairings in my input. So I'm going to apply it at that. I'm going to apply it at that 3-word pairing. And I'm going to get my outputs over here, which is this vector up top here. Then I'm going to slide over and I'm going to say, well, I'm going to take my next set of 3 words, but I'm going to multiply it by the same W. And this was where convolutions became really, really important in the literature, again, for things like images and text, because that W is used at all points in my string. Okay, that is parameter sharing. It's something that modern neural networks did not do. Okay, when you have a big neural network that's just doing a feed forward operation, it does no parameter sharing. And that's why you have really, really large neural networks and a lot of parameters. In this case now, instead of having to represent this as a dictionary sized by D representation, I can just look at K, which is 3. So the number of weights in this matrix has dropped significantly than if I was actually just processing the entire sentence at once. But we know that that's not going to lose information, because what we've been saying this whole time is that I actually don't care where this fits in the rest of the sentence. All I care about is that I can find 3 words together. Okay, and so this weight sharing is in this case a useful assumption. That's not always going to be true. It's only going to be true in cases where this invariance is actually helpful. All right, and so this is how we start to embed, they're called inductive biases, into our networks. You make these architectural decisions, which are actually, in the big scheme of things, slightly unhelpful. Convolutional neural networks are limiting because they have to share their weights. Okay, they have to use the same W at all points in those 3-word strings. But if that assumption is actually true, that I'm not losing information when I force the neural network to work that way, then it actually ends up being useful, and it means that I can learn a lot quicker. Okay, so again, that's an inductive bias in my network, and convolutions are invariant, or at least equivariant. That's their inductive bias. Again, just to highlight the notation, you're filtering in each word one at a time. So that's your embeddings over here. Your vector size, you've already chosen your embedding space. That's D. We chose that as the hidden layer of word to vec. You have K, kernel size. That's the number of words I'm looking at any given time. And then lastly, M, number of filters. How many phrases do I care about finding in my text? Okay, we've gone through all of this. Okay, and again, we said that every column in my weight matrix here is going to be doing a dot product with my input, my concatenated inputs. And so you're going to get large individual values for the response to that filter every single time in that space. Okay, I know there's a lot of information. We have like 3 minutes left. I'm going to try just wrap up a few more ideas here, and then we will we'll kind of call it there today, and I'll wrap up the last few slides next week. So again, there are a couple decisions to make with these convolutional kernels. Okay, The one is, again, this kernel size, this parameter up here, which is k, all right? So the number of words I'm looking at any given time. Now, why might we want to use different kernel sizes? Well, again, the bigger the kernel, the more words I'm going to be looking at any given time, all right? But at the same time, the more variance in those phrases I can get and the less parameter sharing I'm going to get, because now I have to learn to work with 4 embeddings instead of, let's say, 2 embeddings, okay? So you want to try and set your kernels to be as small as you possibly can, all right, without then losing that spatial information and without kind of limiting or restricting your network too much. Okay, so kernel size is the number of input tokens a convolution looks at each step. And so, for example, if you're looking at 2 words, that works very similar to a bigram, which we spoke about earlier, right? We're looking at words like, or phrases like not good, all right, or do like, or the cat. Whereas a 3-word convolution, you're looking for phrases like, such as, like the cat, okay, or I am happy. So now you can see that there is a benefit to maybe moving to a 3 kernel size instead of a 2 kernel size, because the phrase I am happy is meaningful in its own right. If I was only looking at any of those 2 words, I am or am happy, you've lost information either about who is happy or what I am. Okay, so in that case, you want to look at 3 words so you know that I am the one who is happy. But if you're looking at a 4 convolution, then it says I am happy because, or I am happy since. That last word wasn't really semantically useful. It's just another kind of grammatical thing that says that I'm going to now follow it with another phrase. So if I wanted to then account for what that phrase said, I am happy because I like the cat and it sat on my lap. Now I'm going to have a kernel size of like 10. The problem with that is now we're verging again on a dense neural network. So when this kernel size becomes the size of your input in its entirety, it is just returns back to a dense, big feed-forward network that has no parameter sharing and doesn't actually have any inductive bias towards reusing features and re-looking for the same phrase within the network, within the input sentence. Okay, and if you're starting to think, well, why don't we have multiple or use different kernel sizes so we can extract different phrases, then that's a good idea. We'll come to that in a second. Then there's another thing which is called the stride. So it's how many steps we take in the input sentence at a time. So the way I've been explaining it now is we look at the first 3 words, then we take 1 word step to the right. So we now look at I like the, and then after that we take another 1 step to the right, which is like the cat. And you can see that we're always overlapping on 2 words at a time, right? Like the is sitting within that convolution there, and the one immediately next to it over here. But maybe we want to kind of only look at different words, but we don't want to do such a small stride. Maybe we have a really, really long sentence, and I want to start to get less values for the sentence at a time. Well, then I can actually jump 2 words at a time, right? And so now instead of looking at pad like the, instead of moving it to just 1 word over, I'm going to move it 2 words over. So I'm going to start with like the cat. You can see now that because I have a stride of 2, but a convolution window of 3, I only overlap on 1 word at a time. If I have convolutions of 3 and strides of 3, then there's no overlap at all, and I'm processing my entire sentence, but now there's kind of chance that I can miss phrases within the gaps. Okay? So again, your stride, then you usually want to use stride of 1 because we don't actually have any good way of knowing how frequent the cadence is going to be on a particular phrase. But here's another way to kind of make your network more efficient. Cool. I think that is a good point to stop because this is means that I can recap this next week for anyone who is feeling a little bit like overwhelmed by this. All right, I'll see you guys next week. This is going to be your lab too, so I do recommend we stay on top of things. But I also appreciate that that was a lot of information today. Guys online, you happy? Any questions? Good, thank you. Hey, how you doing, mate? Sorry, can you just give me a second to stop the recording?